Hello, welcome back to our online lecture of design of mechanical components. Today, let's talk about the mechanics inside a beam. Let's first take a look at this beam problem. We assume along the z direction there's nothing different, so we can reduce a 3D beam problem to a 2D beam problem like this. From here, you can see we align this beam with the x-axis, and also here is your y direction. We would like to know what's gonna happen if there is a small portion of the beam material when the beam is under some kind of loading from the top. And this position is located at the x direction, having an x distance away from the origin of the coordinate system. And this small portion has a tiny width, dx, very small. So let's focus on how what does this small portion of the material look like if we zoom in and take a look. So this is the small portion of this material, and because of the external load, there could be having some bending moment and shearing force that is applied to the material. So since we want to derive the general equation of the relationship between shearing force, bending moment, and also external load. This is the general configuration. Okay, and we are trying to follow the direction of the moment and shear based on the drawing. Of course, you can derive this based on different configuration. For example, the moment on the right hand side could be clockwise, then the moment on the left should be counterclockwise. So make sure when you try to solve a problem like this, you need to define your initial configuration. No matter what direction you specify, it's okay actually, because if you specify this moment clockwise, but at the end, in fact, the moment applied to this material on the right hand side is actually counterclockwise, then you will get negative value for your m. Okay, so what happened about what's this? What happened to those dv and dm? What does that mean? That means this material is not only under the shearing force and bending moment on both ends, it's also under some kind of external load, like the figure that I'm showing here. So this is causing some kind of difference from both ends of the material, but we don't know how much different. Okay, if we compare to what we studied in the previous lecture, we don't have external load, we just have pure bending from the side or twisting from the side. So supposedly inside the entire material, everywhere is under pure bending or pure twisting. So everywhere the loads are the same. But right here, because of this external load, could be changing everywhere. So this beam is now under a more complicated load condition, and the bending and shearing will be different everywhere. We want to know, since they could be different everywhere, we need to know how are they different at every position. So this is a general position at a distance of x away from the origin. Sorry, and we are just cutting a slight width and try to analyze what's going on. And even the width is so small, there could be change of shearing force and bending moment within this small portion. Okay, so we assume from left to right, the shearing force has increased by dV. And from left to right, the bending moment has increased by dm. So that's the increment of shearing force and the increment of bending moment. Is it always increasing? No, it could be decreasing. But in this configuration, we just define dV as a positive mathematical symbol right here. But if in fact the force is decreasing, at the end we will get negative value for dV. So that's totally fine if you define this as plus. Okay, so based on this configuration, we can now try to solve a balance of force and balance of moment. Let's start with balance of force. Now before we start, we need to understand what's going on from the top. So above this beam, there's a profile of external load. It's a distributed load, and it's having a function of Wx, which means this distributed load is having a magnitude of W, and the magnitude is related to the position of where you analyze. So right here we are analyzing at the position of x. Then the external load, the distributed load, is having a magnitude of W. That's why we have W here. But how come over here there's no difference? How come it's flat? Because we are analyzing a very very small portion with very thin width. So we assume at the top, this distributed load is having the same magnitude. Okay, so this is very thin, a small cut. So the unit of W is Newton over meter. So it's like a line force. It's not pure force. It's how much force you have per unit length. Okay, so how do you calculate the total force? You just multiply the width. Then you will get how much total force you have. So that's why we have a W dx right here. We are multiplying the width, which is dx. So this will be the total external force from the top due to the distributed load. And how many more forces are there facing facing up? Here's one, V. V is facing up. So this will be balanced by the force on the right hand side, which is going down, V plus dV. So from here we can already get a new equation indicating W equals to dV over dx. Then you can calculate how much increment of the shearing force based on this equation. If you do an integral of, if you move dV to the left and do an integral, you can calculate how much shearing force you have. Okay. Now let's do the balance of moment. So over here we are focusing on the clockwise moments. V plus dV is making a rotation clockwise about the center. So the distance from the center to this force will be half of dx. So this is the clockwise moment due to the V plus dV. And also V is making a clockwise moment, and the distance is also half of dx. N is a clockwise moment. Over here we have counterclockwise moment, dN plus dm. How about W? Is it making generating any moment? Yes and no, because it's on the left hand side. The left hand side portion is making a counterclockwise moment, and the right hand side moment is making a. Sorry, I made it. I say it wrong. The left hand side ones are making a clockwise moment, and the right hand side one are making a counterclockwise moment, and they are the same, so they balance out. Or you can treat this as a concentrated load at the center, which is passing through the center of the material, so there's no distance away from the center. That's why it doesn't cause any moment. Okay, and then we clean up this equation. We end up with V equals to dm over dx. Okay, so we can calculate how much. Once we know how much shear we have, then we can calculate how much moment we have. We just need to do some integrals. Okay, very good. Now let's focus on another. Hold on. Let me see when I want to introduce this. Yes, we need to talk about this first. Then we can talk about this part. Okay. We need to know what is y. What is y? Okay. Y is so-called a deflection. So whenever there's a general portion like this being bended, being sheared, it will deform a little bit. So in this configuration, we don't talk about how much deformation is generating, but in the bottom figure, in fact, after those external loads, it will deform, and is kind of like we are holding this left hand side, and we will take a look at the right hand side, and we will see, due to this kind of bending, we will have movement of this right hand side point moving up a little bit due to bending. So we call this dy deflection. So if we bend this beam and this portion is having a slight increment on height, dy, a little bit, then if we sum them up from left to right, we can know what's the total deflection of this beam. Okay, and what we are going to do right now is to estimate what's the dy onto this material, and we will focus on some geometrical properties and also some equations that we learned in the past. First one, we will take a look at this part, c d theta over dx. So where is c? C is half of the height, that would be your c, and d theta is right here. Okay, this is d theta. Okay, so this is basically the angle of this this tilt. Okay, the angle of the tilt, and due to geometry, this portion, this angle is the same, also d theta. So c d theta will be this width, because if you have c, this is like a radius, and this is the angle d theta. Okay, here is d theta, so here should be d theta as well. Okay, I think I okay, there was a mistake, sorry. Here is d theta, this whole thing, and although it looks similar, but here is theta and this is d theta, because we are always drawing this in a very dramatic way, but this d theta will be very small. You won't see it. It's very tiny angular difference, very tiny. So that's d theta. But what is theta? Theta is like for every tiny material, it's having a very tiny contribution on the angular deformation. But overall, if you see the whole beam, it's having a curvature. And then it becomes an arc shape. So the radius of the arc is rho right here. Is the radius of the curvature. And if it's a curvature and it's like an arc, theta is representing where it is. Okay, so if you draw a horizontal line and tangent to the arc of the bended shape, there's a angular difference between this horizontal line and this curve. So that would be overall, when you visualize it, you can see it. There's a theta. And this shape right here, it only this is so tiny portion of it, it contribute a little bit. So d theta is a small contribution of that overall theta. Okay, so let's get back to here. Originally, this geometry is having the length of x, dx. Originally, the width is dx. After you bend it, you would like to know how much length it has increased. So this portion CD theta is the increment of length, CD theta, because it's lengthened a little bit, right, from dx up to here. So CD theta was calculated by, here's C, and here's d theta, like I just showed you. Here's d theta, but due to geometry here, it's also d theta, not theta, but d theta. Okay, so this tiny increment right here is the increment in length. And if you divide it by the original length dx, that would be strain. Okay, and strain is also having a equation of sigma over Young's modulus, and also sigma is also known as mc over I, because we already did it in the last lecture. So from these, we can reduce the equation to here. C was cross out, those C's disappear. So d theta over dx equals to m over ei. Okay, that would be a very important equation right here, because this is how you can, these three equations are how those three could be linked together. W linked to V, V linked to M, M linked to theta. This is how they are linked together. So let's see. The next step is how to link theta to y. Okay. So how do we do that? We do the following right here. Another geometrical relationship. Let's talk about the curvature that we generated due to bending. And if we multiply if we use this radius rho, and then times this angle d theta, we ends up with this, the arc length over here. And because this is right at the neutral axis, so we know at the neutral axis there's no difference on length. So this arc is also having the length of dx. That's why we have rho d theta equals to dx. Okay, And at the end, d theta over dx equals to 1 over rho. Okay, that's important for later derivations. Now, how about this one? Theta equals to dy over dx. Let's take a look. If you take a look at this one, you'll see a small triangle here, a very small triangle. And the angle right here is theta. Okay, and the height is dy. We define this as a increment of deflection. And the horizontal line is the same as dx, right, up to here. And since this triangle is very thin, so theta is almost the same as tangent. And the tangent basically is theta is very close to tangent theta, and tangent theta will be equals to dy over dx. This is how you get theta equals to dy over dx. Okay? So let's take a derivation on top of theta, because earlier right here we have d theta over dx. So at the end, d theta over dx equals to second derivative of y with respect to x. Okay, and this guy, due to the equation we have earlier, this is rho 1 over rho, and also from this equation, d theta dx also equals to m over ei. Then we come up with a very important equation, which is y, second derivative of y with respect to x equals to m over ei. This is how you link y to m, and we can rewrite this in this way. M could be calculated by ei multiplying y double dot. Okay, second derivative of y over with respect to x. And we also have two equations right here. This is telling you if you do one more derivative of m, you get v. You get the shear force. So we do that from the first equation to the second one. V ends up with ei times third derivative of y with respect to x, and one more derivative of v, you get w. So w equals to ei times the fourth derivative of y with respect to x. Okay, so we end up with this. But usually when we solve problems, we usually have knowledge of the external force. We know how much distributed load we have. So it's like we have this information right here. So we can take 4 integrals, we get y. Okay? Or if we once we have y, we can or if we only take one derivative from w, take one integral, we get v, and take one more integral, we get m. Okay, and 2 more integral, we get y. This is how those 4 informations are linked. Y is having this second derivative relationship with m. One more derivative, we have v. One more derivative, we have w. And if we do integral onto the w, we get v. One more integral, we got m. 2 more integral, we get y. Okay, so this psi is very important. I wish you could have better understanding of this. You may not need to derive it during the exam, but I would like you to practice it, so later on when you use it, you can understand how those equations were being generated. Now let's move on to a chef problem. And we have talked about this configuration earlier. It's it's a bending plus twisting condition of a shaft, and if we analyze the somewhere on the top of the material, we will end up with a stress analysis like this. Okay, and from here we would like to know whether this material is under too much load or not. So we need to calculate how much stress and torque we have. But in order to do that, we need to know moment and torque. Okay, so when a beam is under more complicated load conditions, M and T cannot be calculated easily. So how do you do that? You can perform force analysis along the beam, like what we did earlier. Due to some external loads, and we need to know how much shear, how much moment that was caused onto that small portion. So with those two very important information, we then can calculate M and T at certain point. Then we can kind of estimate what's the stress and the tau at the material, and afterward we can consider its safety and to check whether this material can be safe. So that's how the left hand side force analysis could be related to the right hand side stress analysis. So let's assume you can already link these two analyses together. Once you have this, what's next? What you can do next is to do Mohr circle analysis. Okay, so this is a time we're going to review the Mohr circle analysis. Okay, so here here's a general configuration that you get from earlier slide, and let's say you already know the magnitude of sigma A and tau A, and when the reason why I specify A is because in this Mohr circle we are going to analyze this material at many different directions, many different positions, and A is one position that we are observing along this current coordinate system. So when you are having a force diagram like this, you make sure you understand what's your coordinate system and you start from it. And you pick up a point, like what I'm doing right now. You pick up a point on one of the surface. So at this surface, at this coordinate system, and at this surface that is perpendicular to X, I'm standing on top of it, and I just observe how many forces are there applied to this point A. And from here you can tell there is a tensional stress and there's a shearing stress right here. So this normal stress is having the magnitude of sigma A. So you can make a drawing like this. The horizontal axis is your sigma, and you assume positive sigma represent tension. And you can have another axis right here, and you just plot out your shearing force, but you need to specify what's the orientation. For positive tau, I wish it represent counterclockwise. The counterclockwise represent, I should say, positive tau represent counterclockwise shearing force, shearing stress. So here this is having a counterclockwise shearing stress, and it's having a magnitude of tau A. So right at the point A is under two stresses. One is sigma A and tau A. They are both having positive magnitude. So you should be able to get a point right here. On the horizontal component is having sigma A, the magnitude of sigma A, and the y component you have the magnitude of tau A. Just plot out the point based on how much stress and shear you have at the point. Okay, then you move on to another point right here on the top. I call this point B. So let's plot out B first. And you can see in this diagram at the point B, there is no normal force on this plane, but there's a shearing force doing clockwise. So since we define the shearing force, if it's positive, it's representing counterclockwise. So since this one is having a clockwise shear, so it should be having a negative magnitude. So we are plotting the B point right here because it's having a negative tau A shearing stress, no normal stress. So that's why it's right on top of this y-axis. There's no normal stress. So we have a B point right here. So the next idea is that whenever you make a rotation inside this force diagram, you are rotating in this Mohr circle double the angle. Okay, so earlier when I move from A to B, if I move from B to C, you can see the low condition right here is exactly the same as A. That's why I'm moving back to this A point. So C and A is sharing the same point. But in the force diagram, I'm only rotating my observing position by 180 degree, but in this diagram I'm already rotating 360 degree. So that's how you can make a circle. And if you rotate 90 degree more, you are moving down to here at the bottom, it will overlap with the B point. So making a complete circle right here is equivalent to making two circles on the right hand side, okay, on the Mohr circle. This is how you generate a circle. And every point right here is representing some position inside the material which is having certain angle with respect to your coordinate system, and it's telling you how much stress, how much normal stress and shearing stress is having. Okay, so now we are very interested in where we have the largest normal stress. So because of this circle, you kind of see there is a point which is having the largest normal stress, and at this point there's no shearing stress. And in the right hand side figure, it's rotating, let's say 2 theta angle. So if you rotate it here by 2 theta angle, then in the force diagram you are actually rotating by theta, half of this angle by theta. So over here we define this coordinate system as x prime and y prime. It's having a angle theta against the original coordinate system, and we call this point D, and the point D is right at the very right edge of this circle, right end of this circle, and this at this point is having the largest normal stress, and we call this principal stress, and this coordinate is your principal stress coordinate. Okay, so if we tilt our head like this and then observe this material in this along this coordinate x prime and y prime, is having the largest stretching stress along this direction. So it's telling you this material, when it's under this kind of loading, in fact is having a largest stress, tensional stress along this direction. So when we try to figure out whether this material could be broken, we should focus on the orientation where it's under the largest load, and we need to make sure whether along this direction and under this largest load is it going to fail. So if this material is not gonna fail along this direction, then this whole material along every direction should be safe. So this concept is so-called the worst case scenario. In mechanical design, we always focus on the worst case. For the material, the largest load condition is the worst case. Worst for the material, because along this direction is having the largest stretching. And if this material can survive under this worst condition, then the whole thing will survive. Okay, that's why we need to find where is the largest tensional force. Okay, what's next? Okay, if we rotate 180 degree from this point to the other edge, we will get reach to the E point. It's having also having a normal stress, no shearing stress, and it's also on this principal stress coordinate. So this is the second principal stress, and it has been drawn right here along the same coordinate, x prime and y prime, and this is our second principal stress. Okay, but in mechanical design, sometimes this S2 won't be necessary, but for some future models, S2 will be needed for calculations. Okay, but that S2 is actually not the most important thing. The most important thing is S1. But for some model, the mathematical model would like to estimate whether this material can survive, and that model requires you to calculate S2, because S1 and S2 represent the circle, right? It's representing the diameter of the circle. So sometimes the calculation of S2 is necessary for future analysis. But from now on, just understand how we get it, and when we use it, you will know why S2 will be needed later on. Okay, now if we rotate this coordinate from this principal stress plane by 90 degree in the Mohr circle, if we rotate 90 degree here, we are actually rotating 45 degree in here, and it's reaching to a different coordinate system we call x double prime and y double prime. Over here you can see the stress condition is having under the maximum shear. At this position F is having the largest shear, but it's still having normal stress, some normal stress, and from F, if you rotate 90 degree here, you are rotating 180 degree down to here. It's still having the same stress, same shear, but the other direction. So the shearing forces are the same, having the same magnitude, and the normal stresses are having the same magnitude. And along this, when you visualize this in this coordinate system, it's undergoing, it's under the maximum shear, the maximum shear. So sometimes the material cannot handle shearing, and for many cases, when many analysis revealed that material failure may occur along the shearing plane, because material cannot handle shearing well. So this is also indicating probably the material is gonna fail along this orientation. Okay, so you also need to know how to calculate the maximum shear, because later on we have a model called the maximum shear model, maximum shearing stress model, and that model requires you to calculate how much shearing stress you have over here. Okay, next. So if you at the beginning we know sigma A and tau A, and you have drawn this Mohr circle. Can we use it to calculate three important things that we have found earlier, S1, S2, and the tau max? Yes, you can by geometry. And over here, tau max is basically the radius of the Mohr circle. So basically, it's the same as this edge over here of this triangle, the tilting edge. So if we study this triangle here, the height is gonna be tau A, and what's the width right here? It's basically half of sigma A. So we can use square root of half sigma A squared plus tau A squared. We can get tau maximum, basically the radius of the Mohr circle. And how about S1? Here is from this center to S1, this is basically radius. How about this part? From this point to the origin, this distance is basically half of sigma A. So if you have half of sigma A plus the radius, you have S1. Or if you have half of the sigma A and then minus the radius, you get S2. So these are the three equations for you to calculate tau max, S1, and S2. Okay, and here is another example, because in the previous example we don't have normal stress at the along the y-axis. So in a more general case right here, let's say if we have some compression stress, sigma B right here. So at the beginning, when you draw the Mohr circle, you have this A point right here and then B point right here, because there is normal stress sigma B, so it's not right on the vertical axis. It's somewhere at the third quadrant. Then your Mohr circle looks like this. So it will vary your calculation a little bit, but no big difference. For tau max, still we are calculating the radius of the circle. So this radius equals to the square root of the height right here, tau A squared, and also the horizontal part right here. So how do you calculate this part? This is basically half of sigma A minus sigma B. From sigma A minus sigma B, you have the total length right here, and half of it right here. Okay, so half of it and square. So once you have radius, how about S1? From this point is sigma A plus sigma B over divided by 2. Half of sigma A plus sigma B. That would be this point. Okay? Don't be confused by the plus and minus. Think about this. If you want to calculate the width, then you use the high value to minus the low value. That's why it's negative. How about plus? You want to calculate a mean value of two values, no matter what it's positive or negative. You want to get the mean value. The mean value is the sum of these two values and divided by 2. You get the mean. This is the average point at the middle. Okay, this is calculated with this is calculating where it is. So this point is half of sigma A plus sigma B. Then you plus the radius, you got S1. If you minus the radius, you got S2. So that's why you have plus here and minus here. And this is basically the radius. Okay? Please try to practice and make sure you understand how to calculate those. Next, let's talk about tensile test. So usually for tensile test is only under a pure stretching. maybe like this, or you can stretch like this. And for tensile test, the Mohr circle is always like this, because along the y direction over here, there's no stress for the whole time, and no shear. So for tensile test, your Mohr circle looks like this, very simple. And the maximum shear stress will be the radius of the circle is actually half of sigma A. So even you are pulling your material under this tensile test, there is still shearing stress inside, but it's over here. So if it's over here, then it's having a 90 degree of angle. You need to rotate by 90 degree, so that means you need to rotate 45 degree. So along this 45 degree plane, that's where you have your maximum shear. So if you pull your material like this, the shearing plane is like a cross, so your material may fail along this direction. Okay, next, this is more general. If you study a 3D case. In this class, we may not do too much on 3D case, but just for you to know, if it's a three-dimensional a problem, there are actually 3 more circles, and each circle represents the 2D stress analysis along a plane. And right here, if we are focusing on the XY plane, then we are having a Mohr circle like this big. But if we have stress along on the other 2 planes, actually the other 2 planes are also having Mohr circle, smaller ones. In this case, because along the third direction there's no stress, so the third principal stress is 0. That's why the other 2 Mohr circles are looking like this. This one is the Mohr circle along the y prime z plane, and it's sharing the S2 and S3 which is 0, and the other one is this guy, the Mohr circle along the x prime z plane, so basically the top plane, and along this plane is sharing the S1 and S3, which is 0, so this circle. Okay, so when you are analyzing a 2D analysis, always think about what's going to happen along the third direction. And there is actually analysis along the third direction, but in our case, mostly we are focusing on plane stress problems. And the reason why we can analyze it in a 2D Mohr circle is because along the third direction there's no stress. So we don't even need to worry about this blue and purple Mohr circles, because we only focus on the XY plane, and the black ones are the ones that we're focusing on if we are analyzing a plane stress problem, only a 2D problem. But be aware, if there's a more complex problem where you have third direction stress in the third direction, the Mohr circle is more complex and it looks like this. Okay, so that's the end of today's lecture, and please review this video multiple times and make sure you understand about the derivations that we have. First, we have a beam problem. We try to figure out what's the shearing force and also bending moment everywhere inside the beam. Once we have it, we derive several equations with derivatives and integral relationships. We need to know how this distributed load can be related to shear force, bending moment, and deflection. So once we know the moment and torque, at every position, we can calculate the normal stress and shear stress everywhere. But how do we know if the material is safe? We need to analyze a force diagram at that position. Since we already know the normal stress and shear stress, we can work on our Mohr circle and make sure this Mohr circle is going to be safe. So in the following lectures, we will tell you, okay, once you know the Mohr circle, we will teach you whether your design is safe or not. If it's not safe, what can we do? Okay, so that's the end of today's lecture. If you have questions, feel free to let me know. You can send me emails or message me in our group. Thank you. Bye bye.